gravitational calculations. So page 56, right, so we have Newton's law of gravitation. We have this just W is equal to mg, wouldn't be too worried with that one. This for the acceleration due to gravity at the surface of an object. That's not relevant to us. This is obviously very relevant to us because we have to be able to derive it. Now, on top of that, remember, you should know v squared is equal to gm over r, which is partly through this guy, okay, and m being the central mass and r being the radius of orbit, gives you the velocity of the satellites. Also, from earlier, okay, you have your centripetal force. It's on page 51, either one. Okay, they will be part of gravitational as well, and there's one more. No, that's about it. Okay, so sorry, the other one is periodic time. Remember, periodic time is 2 pi r over v. We've looked at how we got that, and again, watch that one because it's not in the tables. Watch this one, clearly not in the tables. These are in the tables, but they're earlier. And then the other versions, t is 2 pi over omega, which is in the tables and an odd spot with simple harmonic motion. But again, exclamation mark, they're the ones to watch. So you've Newton's law of gravitation, your centripetal force, both methods, periodic time, you've the expression for acceleration due to gravity, small g, you've the speed of a satellite, which you have to learn, and your periodic time, I would suggest you learn that one as well. Okay, so that's what we're using, and I'm going to go through a few questions now. Okay, so this is the first one, so let's have a look at this. So I've cut out the calculations, the bits that are not calculation, and covered everything else, okay, in this question. So this is a past paper. Okay, so calculate the angular velocity, okay, calculate the angular velocity and the linear velocity ISS. So let's go through what we've been given. Okay, so International Space Station Total Functions Research Laboratory, ISS orbits the Earth at an altitude of 4.13 by 10 to the power of 5 meters. So the height above the surface, 4.13 by, sorry, you can see it, 4.13 by 10 to the power of 5. And the periodic time is 92 minutes 50 seconds. Now I will always sketch this as we go. Okay, so sketch. So we've the satellite up here, and we've been given, that the height of that is 4.13 by 10 to the power of 5. Okay. Now down here we're given the mass of the ISS is 4.5 by 10 to the power of 5. Now remember, that's the satellite, and the radius of the Earth 6.37 by 10 to the power of 6. Sometimes we're given that in kilometers. We're going to put that in here as well, 6.37 by 10 to the power of 6. And it should be clear from your diagram now that adding the two of them gives you the radius of orbit. Okay, so remember, the radius of the orbit is the center of the central body, always relevant. Okay. Now, so you're asked for your periodic. You've been given the periodic time, and you're asked for the angular velocity. So let's go back to your formula, and this is where it's not just gravitational. Okay, you have a formula that just links periodic time and angular velocity. That one, isn't it? Okay, that one. Right, and this is one of your fancy formula, which is only two variables. So if you have angular velocity, you have periodic time. Now, we need to get the angular velocity, we need to get this in seconds. So 92 by 60 plus 50 comes out at 5,570. So to get the angular velocity, we just have 5,570 is equal to 2 pi over omega. Okay, so rearrange, omega is 2 pi over 5,570. I have to decide here now, which is bad practice. I'm going to run out of paper otherwise. 1.1 by 10 to the power of minus 3 per second, or radians per second. Per second or radians per second, both perfectly acceptable. Okay, everybody happy? Alright, so that's that one. Second part, it says the linear velocity. Okay, so you want to get the linear velocity. So to get the linear velocity, so that's part 3. Parts 1 and 2 were just straight off notes. That's 3a, this is 3b. Okay, you're asked for the linear velocity. Okay, so we now have the angular velocity, So we're going to write this into our list. Okay, and to get the linear velocity, well, we have the angular velocity, and we have the total radius, which is add the two of these together. Okay, so I'm going to do radius of orbit up here is 6.37 by 10 to the power of 6 plus 4.13 by 10 to the power of 5. Okay, and we get 6.78 by 10 to the power of 6. Clearly, you'd have done that. That's the radius of orbit. Okay, I'm going to put it in here as well because it's going to be handy. Okay, so we have our formula. V is equal to r omega. Okay, to relate linear and angular velocity as long as you have the radius of orbit. So we're in business. So 6.78 by 10 to the power of 6 multiplied by our angular velocity, which we just got. Okay, and we get an answer there of 7,650 meters per second. Okay, 7,650 meters per second. Okay, so just to recap, okay, to get the angular velocity, we had the periodic times, we were in business. To get the linear velocity, we have the radius of orbit, and always look for radius of orbit, and we have the angular velocity, so we're in business. Okay, part 5, name the type of acceleration the ISS experiences travels around the circular orbit. What force provides the acceleration? Well, the acceleration is centripetal. Acceleration, you get away with acceleration through gravity, but we're looking for the rotation. Okay, and it's provided by the force of gravity. Okay, we move on to part 5. Calculate the attractive force between the Earth and the ISS, hence or otherwise calculate the mass of the Earth. Okay, now to get the attractive force between the satellite and the Earth, now remember that's the gravitational force, but it is also the centripetal force. Okay, so you'd struggle to get the gravitational force. You can't get it from what we have here using Newton's laws or anything like that. Newton's law of gravitation, so we have to look the other way. But we have the mass of the ISS, the mass of the satellite, we have the velocity of the satellite, and we have the radius of orbit, so we're in business. Okay, so we're going to use F is equal to mv squared over r. Okay, so in this case the mass is 4.5 by 10 to the power of 5. The velocity is 7,650 squared, and the radius of orbit is 6.78 by 10 to the power of 6. A lot of thinking going on in this now. Okay, and you end up with 3.884 by 10 to the power of 6. Okay, newtons. Part 6. They ask you if the value of the acceleration of gravity, hence or otherwise calculate the mass of the Earth. We're still in part 5. Hence or otherwise calculate the mass of the Earth. Okay, so several ways of doing this. Okay, but since it's hence, okay, we've been given the force, so the logical thing, we'll do the hence. Okay, so F is equal to G m1 m2 over r squared. Okay, we have the force, which is 3.884 by 10 to the power of 6. We have the universal gravitational constant. I put it in here now while we have it, but that's in your tables, you know that. 10 to the minus 11. Okay, you don't have one of the masses, but you have the second mass, the mass of the ISS, 4.5 by 10 to the power of 5. And the radius of orbit, again, 6.78 by 10 to the 6 squared. Excuse me, I won't go into the maths of that. Okay, so just a bit of rearranging. So it comes out at 5.95 by 10 to the power of 24. If you don't get that, if you're trying this at some stage, if you don't get it, send me a text. Okay, now part 6. Okay, if the value of the acceleration of gravity in the ISS is 8.63, why do occupants of the ISS experience apparent weightlessness? Okay, now this is, remember we've looked at this before. Okay, the people in the ISS are accelerating due to gravity, and we've seen your man singing yesterday, accelerating due to gravity towards the Earth's surface at 8.683 meters per second squared. But the ISS is also accelerating due to gravity at the same rate. So therefore the acceleration due to gravity of the astronauts relative to the station is 0, and they experience weightlessness. Okay, so the easy way of answering that is the acceleration due to gravity of the astronauts is equal to the acceleration due to gravity of ISS. Okay, that's the way of answering it. Okay, and that's a common enough answer. Now there's another answer which is an awful answer where you say they're in free fall. Don't like it, but anyhow, to leave it there anyway for you. Okay, part 7. Okay, geostationary communication satellite orbits the Earth at a much higher altitude than the ISS. What is the period of geostationary communication satellite? And this is crucial. You have to know this. You have to remember it. You know the period. Okay, a geostationary satellite has to stay in the same position above the Earth's surface all the time. The Earth rotates once every 24 hours, so the geostationary satellite must rotate once every 24 hours if you want to stay in the same spot. If you're using your Sky satellite dish, you need the Sky satellite to be in the same spot above you all the time. Your dish is rotating once every 24 hours. You need the geostationary satellite to do the same. Okay, so 24 hours. Remember that one. It's important.